Your USB drive remembers. The sun burns. Your phone glows blue. Carbon dating tells us when something died. GPS knows where you are. Your body runs reactions at insane speeds. The scanning tunneling microscope sees atoms. Every single one of these things breaks the rules of physics as we understood them before 1928. These are atomic tricks, so impossible that classically they cannot happen. Particles passing through walls, they don't have energy to cross. Protons fusing at temperatures far too low. Electrons jumping energy gaps to create light. Without these quantum impossibilities, the sun goes dark. GPS fails in minutes. Your electronics stop working. 7 atomic phenomena that should not exist but power everything you touch. Which one keeps you alive right now? Each gate traps electrons behind an insulator so thin, 9 nanometers of silicon dioxide, that classical physics says it's not thin enough to hold anything. Those electrons should stay trapped for a century. Instead, quantum tunneling lets them leak through the barrier at a rate so precisely controlled that your data survives for 10 years but can be erased in milliseconds when you want it gone. 1967. Bell Labs. Dao Kong and Simon C. published the first floating gate non-volatile memory device in the Bell System Technical Journal, dated July 1967. They explicitly use Fowler-Nordheim tunneling equations, math describing how electrons tunnel through barriers when you crank up the electric field. The arrow in their diagram shows direct tunneling of electrons through silicon dioxide into a conducting island, surrounded by insulator. At the time, nobody knew this would become the foundation of flash memory. 1970 to 1976. Multiple labs chase silicon nitride storage and floating conductor concepts. Experiments with metal gate silicon nitride, silicon dioxide, silicon devices. Various permutations. But the barrier is too thick or too leaky. Then, 1976. Hughes Microelectronics in Newport Beach, California. Eli Harari, who spent 1969 to 73 researching thin film silicon dioxide and tunneling phenomena for his PhD thesis at Princeton, shows that if you make the oxide thin enough, around 100 angstroms instead of 700 to 1000, electron conduction becomes efficient and reliable. The trick is Fowler-Nordheim tunneling. Electrons don't need to climb over the barrier, they quantum tunnel through it. The thinner the barrier, the higher the probability. Harari files the patent on November 5, 1976. Priority date, locked. By 1978, floating gate EEPROM with thin oxide and Fowler-Nordheim tunneling for both program and arrays is proven reliable at Hughes. This becomes the ancestor of flash. Support our work. Also comment from which city you're hearing this from. Also, this script is researched and factual using sources from the Engineering and Technology History Wiki Milestone on the floating gate EEPROM published in August 2025 and corroborated by the original Kong and C paper from Bell Labs Technical Journal, July 1967, and Harari's U.S. Patent 4253059, filed November 1976. Now back to the information. Time, milliseconds. Erase reverses it. Electrons tunnel back out. Classical barrier height, 3 electron volts. Electron energy in the substrate, way less than 3 electron volts. Yet the electrons cross. The probability decreases exponentially with barrier width and height. At 9 nanometers with high field, the probability is just right. Make it thinner and the data leaks. Make it thicker and you need dangerously high voltage, or the write takes too long. 9 nanometers is the engineering sweet spot where quantum mechanics becomes a product. 2025 data, all NAND flash and most NOR flash rely on tunneling through silicon dioxide films at approximately 10 nanometers or 100 angstroms. Global flash memory market exceeds $100 billion per year. Every USB stick, every solid-state drive, every smartphone powered by electrons doing the impossible. The data on your drive right now exists because about 19 trillion electrons are trapped in floating gates by barriers they're simultaneously forbidden and allowed to cross. Your enzymes do it at body temperature. In a test tube at 37 Celsius with the same chemicals but no enzyme, the reaction takes years. The enzyme completes it in milliseconds. For decades, biochemists assumed enzymes just lower the activation energy by stabilizing the transition state. Classical transition state theory. Atoms hop over a barrier. Simple. 1980s onward, kinetic isotope effects don't match predictions. Replace hydrogen with deuterium in the substrate. Deuterium is twice as heavy. And measure how much the reaction slows. Semi-classical theory predicts an upper limit on the hydrogen over deuterium rate ratio. Experiments blow past that limit. Bovine serum amine oxidase, yeast alcohol dehydrogenase, soybean lipoxygenase 1. All show hydrogen over deuterium ratios larger than semi-classical models allow, and with temperature dependence that screams tunneling. Judith Klimman's group at UC Berkeley nails it. Published in the Journal of the American Chemical Society in 2002, soybean lipoxygenase 1 transfers hydrogen from a carbon-hydrogen bond to an iron center. Measure the rate with protium. Measure with deuterium. Measure with tritium. The mixed Swain-Schad exponent, a diagnostic for tunneling, exceeds the semi-classical limit of 3.3. It hits 4.3 in some enzymes. That means the hydrogen nucleus is quantum tunneling through the reaction barrier rather than hopping over it. Quantum mechanics says the hydrogen wave function extends beyond the donor atom. If the donor-acceptor distance fluctuates to just the right value and the energy levels align, a tunneling-ready state, the hydrogen nucleus can appear on the acceptor side without climbing the barrier. This happens in femtoseconds. The enzyme uses protein dynamics to sample distances and gate the tunneling. Experiments with mutants far from the active site still change the tunneling rate. Why? Because distal mutations alter the frequency of vibrations that bring donor and acceptor into tunneling range. It's environmentally coupled hydrogen tunneling, published by Knapp and Klinman in the European Journal of Biochemistry in July 2002. Aromatic amine dehydrogenase and other flavoproteins proceed purely by tunneling with negligible classical contribution when breaking stable CH bonds. A 2006 study published in Natural Sciences by Wodka and others demonstrated resonance-assisted tunneling in carbon monoxide bound to sodium ions. Replace carbon-12 with carbon-13 or oxygen-16 with oxygen-18, and the reaction rate changes by factors larger than classical kinetics predict. The isotope effect is non-intuitive. Heavier nuclei have smaller de Broglie wavelengths, so they tunnel less efficiently. The enzyme exploits this to control which bonds break. In your body right now, alcohol dehydrogenase in your liver, breaking down ethanol, lipoxygenase, enzymes managing fatty acid metabolism, methylamine dehydrogenase, processing nitrogen compounds, all rely on hydrogen tunneling. Turn off quantum mechanics, and these enzymes slow by factors of 10 to 1,000. Metabolism stops. You die. The trick is that life evolved active sites with the perfect geometry and dynamics to maximize tunneling probability while maintaining specificity. Enzymes are quantum probability amplifiers. The Sun has 1/7 of that. The barrier, the Coulomb barrier, arises because both protons carry positive charge and like charges repel. At 15 million Kelvin, protons have average kinetic energy around 1.3 kilo-electron-volts. The Coulomb barrier height is several hundred kilo-electron-volts when the protons are nuclear radius close. Energy shortfall, 2 orders of magnitude. Classical physics says fusion cannot happen. The Sun should not shine, but it does. 38 times 10 to the 26 watts. Constant for 4.5 billion years. What's missing from the classical picture? Quantum tunneling. Protons are not billiard balls. They are quantum particles with wave functions that extend into classically forbidden regions. When 2 protons approach each other, their wave functions overlap. Even when the protons lack enough energy to surmount the Coulomb barrier, there's a non-zero probability the wave functions penetrate the barrier and the protons find themselves close enough for the strong nuclear force to bind them. This probability is tiny. 1928, George Gamow at the University of Göttingen applies newly developed quantum mechanics to alpha decay, alpha particles escaping atomic nuclei by tunneling out through the Coulomb barrier. Same math applies in reverse. Nuclei can tunnel in through the barrier. By the 1930s, Arthur Eddington advocates that proton-proton fusion via tunneling power stars. The math checked out. Enough to bind. It's insanely rare. For any given pair of protons in the Sun's core, the probability of successful fusion is about 1 in 10 to the 28th, roughly the same odds as winning the Powerball lottery 3 times in a row, according to calculations published by Ethan Siegel in Big Think in January 2025. But the Sun has 10 to the 56 protons. Even at 1 in 10 to the 28th odds, enough protons tunnel and fuse every second to generate the Sun's luminosity. The average proton in the core waits 9 billion years before successfully fusing. That's why the Sun burns steadily rather than exploding. The rate-limiting step is this first quantum tunneling event. Once deuterium forms, the next steps are fast. Deuterium plus proton goes to helium-3 in about 1 second. Helium-3 waits around 400 years, then fuses with another helium-3 to make helium-4 plus 2 protons. Net result? 4 protons become 1 helium-4 nucleus, releasing 26.7 megaelectron-volts of energy per fusion. Without tunneling, this chain never starts. The Gamow factor quantifies the tunneling probability as a function of temperature and nuclear charge. For the Sun, the Gamow factor calculated for 15 million Kelvin and proton-proton collisions gives a tunneling enhancement of about 10 to the 40 over classical expectations. That factor is why stars shine. Published analysis in the European Physical Journal in 2012 and corroborated by NASA and multiple astrophysics textbooks. A 2025 study titled Most Stars Shouldn't Exist, published at evansism.com in July points out that stellar core temperatures are insufficient by classical standards, yet 95% of stars in the universe have cores cooler than the Sun, all powered by quantum tunneling. Turn off tunneling and every star goes dark. Earth freezes. Photosynthesis stops. Life ends. The photons hitting your skin right now originated in a quantum tunneling event in the Sun's core that happened 30,000 to 1 million years ago, the time it takes for energy to random walk out of the core to the surface. But here's the problem. The atomic clocks on GPS satellites don't tick at the same rate as atomic clocks on the ground. Einstein's special relativity says clocks in motion run slow. The GPS satellites orbit at 14,000 kilometers per hour. Time dilation formula from special relativity predicts the satellite clocks should lag behind Earth clocks by about 7 microseconds per day. That's 7 millionths of a second. Doesn't sound like much. But multiply 7 microseconds by the speed of light and you get 2.1 kilometers of position error per day. After 2 minutes of operation, GPS would be useless without correction. Then there's general relativity. Clocks in stronger gravitational fields run slower. GPS satellites orbit at 20,000 kilometers altitude, where Earth's gravitational field is weaker than at the surface. General relativity predicts the satellite clocks should run faster by about 45 microseconds per day due to gravitational time dilation. The two effects don't cancel. Special relativity slows the clocks by 7 microseconds per day. General relativity speeds them up by 45 microseconds per day. Net effect. The satellite clocks gain 38 microseconds per day compared to ground clocks. Published calculations by Neil Ashby in Physics Today in 2002 and corroborated by the U.S. Naval Observatory. The factory offset exactly compensates for the combined relativistic effects. When the clocks fly in orbit, the relativistic speedup brings them back to 10.23 megahertz, as measured in the Earth-centered inertial frame. Brilliant. This correction was implemented in the very first GPS satellites launched in the late 1970s. The GPS system is a working validation of Einstein's relativity. Ignore relativity and GPS fails. A 2023 article in GPS World titled Inside the Box, GPS and Relativity explains that without relativistic corrections, GPS receivers would accumulate up to 11 kilometers of error per day. After 2 minutes, the common bias would make the system unreliable. Field tests confirm this. In 1977, experimenters turned off the relativistic correction on a test satellite. The onboard clock drifted exactly as relativity predicted, confirming 38 microseconds per day of gain. Today, all GPS satellites use the factory offset, and additional corrections handle orbit eccentricity. The fact that orbits aren't perfectly circular means the velocity and gravitational field vary slightly over the course of each orbit, producing periodic timing corrections. Every time you use GPS or GLONASS or Galileo or Beidou, you're relying on relativistic time dilation effects measured to nanosecond precision. The coordinates on your screen depend on Einstein's equations written in 1905 and 1915. The universe obeys relativity whether we like it or not. GPS proves it every second. As published by the International Association of Physics Students in March 2023, GPS requires corrections for special relativistic time dilation minus 7 microseconds per day and general relativistic time dilation plus 45 microseconds per day with a net gain of 38 microseconds per day. Without these corrections, navigational accuracy degrades from 5 meters to kilometers within minutes. To support our work. Also, comment from which city you're hearing this from. Also, this script is researched and factual using sources from Neil Ashby's paper Relativity in the Global Positioning System, published in PMC Article 5.2, 5.3.894, and the U.S. Naval Observatory papers GPS and Relativity. An engineering overview by Flegel and D'Espositi from 1996, and the GPS World, October 2023 article. Inside the box, GPS and Relativity. Now back to the information. The carbon-14 in your tissues starts decaying. Measure how much is left and you can calculate how long ago the organism died. This is radiocarbon dating developed by Willard Libby at the University of Chicago in the late 1940s. He won the Nobel Prize in Chemistry in 1960. But here's the quantum trick. Carbon-14 has 6 protons and 8 neutrons. It's unstable. One of those neutrons needs to convert into a proton to reach a more stable configuration. The conversion happens via beta decay. A neutron inside the carbon-14 nucleus transforms into a proton, emitting an electron and an electron antineutrino. The electron, called a beta particle, shoots out of the nucleus with a maximum energy of 156 kilo-electron-volts and weighted mean energy of 49 kilo-electron-volts. The problem is that inside the nucleus, the neutron is in a bound state. To decay, it must tunnel through the nuclear potential barrier. This barrier arises from the strong nuclear force holding the nucleus together. Classical mechanics says the neutron is stuck. It can't escape its bound state to undergo decay. But quantum mechanics allows the wave function of the neutron to penetrate the barrier. Over time, there is a finite probability the neutron wave function overlaps with configurations that allow weak interaction decay. When it happens, the neutron becomes a proton. The beta particle and neutrino carry away energy and momentum, and carbon-14 becomes nitrogen-14. The half-life, 5,730 years, is the timescale over which half the carbon-14 nuclei in a sample will have undergone this quantum tunneling decay. Authenticity, Turin shroud, determined to be made between 1260 and 1390 AD, not first century, and countless archaeological sites. The method works up to about 60,000 years, because beyond that, the remaining carbon-14 is below detectable levels. Beta decay is measured either by counting the beta particles emitted using a Geiger counter or gas proportional counter, or by accelerator mass spectrometry, which counts the carbon-14 atoms directly. AMS became standard in the 1990s. It requires only milligrams of sample instead of grams and gives results in hours instead of days. As published by the University of Chicago News in June 2025, Libby established that living organisms have 14 disintegrations per minute per gram of carbon. When the organism dies, the decay rate drops exponentially with half-life, 5,730 years. Libby's first graduate student, Ernest Anderson, established in the 1940s that organic materials contain essentially the same natural abundance of radiocarbon at all latitudes from pole to pole. This uniformity makes radiocarbon dating globally applicable. The quantum process underlying all of this is beta decay via weak interaction with the decay rate, determined by tunneling through the nuclear barrier. Without quantum tunneling, there is no beta decay. Without beta decay, there is no radiocarbon dating. Archaeologists would have no way to date organic artifacts. History would lose a crucial chronological tool. Every radiocarbon date you see in a museum or textbook exists because neutrons and carbon-14 nuclei quantum tunnel through barriers they classically cannot cross. In quantum mechanics, electrons and solids exist in allowed energy bands separated by forbidden gaps. The valence band is where electrons are bound to atoms. The conduction band is where electrons are free to move and conduct electricity. Between them lies the band gap, an energy range where no electron states exist. When you apply voltage across a p-n junction in a semiconductor, electrons from the n side flow into the p side and recombine with holes. Each recombination releases energy equal to the band gap. If the semiconductor is a direct band gap material, the energy comes out as a photon. The photon's energy equals the band gap energy. The photon's wavelength is determined by the equation wavelength in nanometers equals 1,240 divided by band gap energy in electron volts. A band gap of 1.8 electron volts gives red light at 690 nanometers. 2.5 electron volts gives green light at 500 nanometers. 3.0 electron volts gives blue light at 413 nanometers. This is why LED color is determined by the semiconductor material, not by dyes or filters. Gallium arsenide has a band gap of 1.4 electron volts, infrared. Gallium phosphide doped with nitrogen gives red at 1.8 electron volts. Gallium nitride gives blue at 3.4 electron volts. The key phrase is direct band gap. In these materials, the electron at the bottom of the conduction band and the hole at the top of the valence band have matching momentum. When they recombine, the energy goes directly into a photon. Momentum is conserved. Energy is conserved. Efficiency is high. Silicon and germanium are indirect band gap semiconductors. In these materials, the conduction band minimum and valence band maximum occur at different momentum values in the crystal structure. An electron recombining with a hole must change its momentum. That requires a phonon, a quantum of lattice vibration, to carry away the momentum. Photon plus phonon emission is much less likely than photon-only emission. The probability drops by factors of thousands. Silicon LEDs exist, but they're dim and inefficient. Most of the energy goes to heat. For this reason, commercial LEDs use direct band gap materials. The first visible LED was demonstrated in 1962 by Nick Holonyak at General Electric using gallium arsenide phosphide, red light. Over the next 30 years, researchers developed yellow, green, and finally blue LEDs. Blue is the holy grail because combining red, green, blue gives white light. The breakthrough came in the early 1990s. Shuji Nakamura at Nichia Corporation in Japan developed gallium nitride LEDs with high efficiency. Published in 1991, blue LED at 450 nanometers, Nakamura, Isamu Akasaki, and Hiroshi Amano shared the Nobel Prize in Physics in 2014 for the invention of efficient blue LEDs. With blue LEDs, you can make white light either by phosphor conversion, coating a blue LED with phosphor that emits yellow, the combination looks white, or by combining red, green, blue LEDs. This enabled LED lighting, LED displays, and LED backlights. As published in MIT News in July 2010 in the engineering textbook Light Emitting Diodes by Schubert, the band gap determines the photon energy, and thus the wavelength and color. Silicon's band gap of 1.1 electron volts is ideal for solar cells, absorbing sunlight but not for emitting visible light. LEDs require band gaps in the range of 1.6 to 3.2 electron volts, corresponding to red through violet. Quantum mechanics dictates the band structure. The Pauli exclusion principle restricts electrons to discrete states. The periodic lattice of the crystal creates allowed and forbidden bands. The band gap is an emergent quantum phenomenon. Without quantum mechanics, there are no band gaps. Without band gaps, there are no LEDs. Your phone screen, your LED bulbs, your laptop display, all rely on electrons jumping across quantum mechanically determined energy gaps to emit photons of precise wavelength. It lets you see individual atoms on a surface, resolution down to 0.1 nanometers. Before STM, the smallest things we could image were hundreds of atoms wide using electron microscopes. Suddenly, we could see single atoms. How? Quantum tunneling. The STM has a metal tip sharpened to a single atom at the end. You bring this tip within 1 nanometer of a conducting surface. At this distance, the electron wave functions from the tip and the surface overlap. Apply a small voltage, typically millivolts, between the tip and surface. Electrons tunnel from the tip to the surface or vice versa, depending on voltage polarity. The tunneling current is exquisitely sensitive to the tip surface distance. If you move the tip 0.1 nanometers closer, the current increases by roughly a factor of 10. This exponential dependence comes from the quantum tunneling probability, which decreases exponentially with barrier width. Scan the tip across the surface in a raster pattern. Measure the tunneling current at each point. Use a feedback loop to adjust the tip height to keep the current constant. The height variations map the surface topography at atomic resolution. The STM doesn't actually see atoms. It detects their electron density. Where there's an atom on the surface, the electron density is higher. The tip height needs to retract slightly to keep the tunneling current constant. That retraction shows up as a bump in the image. The result is a three-dimensional map of atoms on the surface. Binnig and Rohrer shared the Nobel Prize in Physics in 1986 for the STM. The Nobel Prize in Physics is awarded to John Clark, John Martinis, and Michel Devoret for experiments in 1984 and 1985 that demonstrated macroscopic quantum tunneling in superconducting circuits. These experiments showed quantum tunneling occurring not just for single particles, but for collective states involving billions of electrons behaving in unison as if they are a single quantum particle filling the entire circuit. Published in the Nobel Prize announcement in October 2025. This opens the door for quantum computers based on superconducting qubits, which use Josephson junctions, devices where Cooper pairs of electrons tunnel through an insulating barrier between superconductors. The tunneling is macroscopic in the sense that the quantum state involves a macroscopic variable, like current or magnetic flux. What makes STM and superconducting qubits possible is that tunneling is not limited to microscopic particles. Under the right conditions, entire systems can exhibit tunneling behavior. Back to the STM, IBM researchers used the STM to manipulate individual atoms. In 1989, Don Eigler and Erhard Schweitzer at IBM Almaden spelled out IBM using 35 xenon atoms on a nickel surface. They used the STM tip to pick up and place each atom. Published in Nature in April 1990, this proved atomically precise manufacturing was possible. Today, STMs are standard tools in nanoscience. Researchers use them to study graphene, measure superconducting gaps, probe quantum dots, and engineer molecular devices. All of this rests on the fact that electrons quantum tunnel through vacuum barriers about 1 nanometer wide. Classical mechanics says electrons cannot cross vacuum gaps. The barrier is infinite. Quantum mechanics says the wave function extends into the barrier. The tunneling current is measurable and controllable. Typical STM tunneling current is nanoamps to picoamps. Voltage is millivolts. The electrons are not thermally excited over the barrier. There isn't enough thermal energy at room temperature. They tunnel, pure quantum effect. A 2025 article in Physics Today discusses how quantum tunneling and scanning tunneling microscopy enables atomic scale manipulation and spectroscopy. The STM has become essential for nanotechnology and condensed matter physics. Without tunneling, we would still be imaging surfaces with electron beams that give resolution limited by wavelength, nanometers, not angstroms. Seeing individual atoms would be impossible. Manipulating them unthinkable. The results were published July 28, 2025. The discovery challenges a century of understanding. Previously, scientists thought electrons could only interact with the nucleus after exiting the tunnel. This experiment showed the electron can gain energy inside the barrier and collide with the nucleus while still inside, strengthening what's known as Freeman resonance. The ionization rate was significantly greater than previously observed ionization processes and barely affected by changes in laser intensity. What this means for future tech: more precise control of electron behavior in semiconductors, quantum computers, and ultra-fast lasers. The authors state, "We can finally understand tunneling more deeply and control it as we wish." Published in Science, Daily, December 14, 2025. This is brand new data. The 100-year mystery of electron tunneling is being peeled back layer by layer. As recently as July 2025, researchers are discovering tunneling is even stranger than we thought. Electrons don't just pass through barriers, they interact with the nucleus mid-flight inside regions that are classically forbidden. That's a quantum trick on top of a quantum trick. Electrons tunnel through insulators thinner than 10 nanometers to store your data in flash memory. Hydrogen nuclei tunnel through reaction barriers, so enzymes in your cells can break CH bonds at body temperature, keeping you alive. Protons tunnel through the Coulomb barrier in the sun's core, allowing nuclear fusion at 15 million Kelvin, instead of the 100 million Kelvin classical mechanics demands. GPS satellite clocks run 38 microseconds per day fast due to relativistic time dilation. Special relativity slowing them by 7 microseconds, and general relativity speeding them by 45 microseconds, requiring precise correction, so your navigation doesn't drift kilometers per day. Neutrons and carbon-14 nuclei tunnel through the nuclear potential barrier, undergoing beta decay with a half-life of 5,700. 30 years enabling radiocarbon dating of organic materials up to 60,000 years old. Electrons and LEDs jump across band gaps in direct semiconductors like gallium nitride, emitting photons with energy and wavelength determined by the quantum band structure, the reason your phone screen glows and LED bulbs exist. Electrons tunnel across 1 nanometer vacuum gaps in scanning tunneling microscopes, creating currents sensitive enough to map. Individual atoms on surfaces with sub-angstrom resolution and enabling atomic manipulation that spelled IBM with 35 xenon atoms in 1989. Decreasing exponentially with barrier width and height. The theory predicted it. Experiments confirmed it. Engineering exploited it. By the 1950s, tunnel diodes existed. By the 60s, floating gate memory. By the 80s, scanning tunneling microscopes. By the 1990s, flash memory ubiquity. Today, quantum tunneling is not exotic, it's infrastructure. Your data, your light, your chronology, your position, your metabolic reactions, your atomic scale science, all powered by particles doing what Newton said they could never do. The universe is stranger than classical intuition. Atoms are not billiard balls. Electrons are not marbles. Particles have wave-like properties. Wave functions extend into forbidden regions. Probabilities rule. And those probabilities, calculated from solutions to the Schrödinger equation with exponential tails leaking through barriers, explain why the sun shines, why you can navigate, why your drive holds data, and why your phone lights up. Without tunneling, the universe is dark, cold, and incomputable. The Nobel Prize in Physics is awarded for macroscopic quantum tunneling in superconducting circuits proven in 1984. October. Quantum tunneling remains an active research frontier. We're still learning. But here's what we know for certain. Flash memory invented by Kong and Say in 67 and commercialized by Harari in 76 stores, data via Fowler-Nordheim tunneling through silicon dioxide barriers around 10 nanometers. Thick. Today's NAND flash market exceeds $100 billion annually. Enzyme-catalyzed hydrogen transfer and lipoxygenase, 1-alcohol dehydrogenase, amine oxidase, and dozens of other enzymes proceeds via quantum tunneling of hydrogen nuclei, through reaction barriers with kinetic isotope effects exceeding semi-classical limits published by Klinman and collaborators starting in the 1990s and continuing through the 2020s. Nuclear fusion in the sun's core at 15 million Kelvin relies on quantum tunneling of protons through the Coulomb barrier with a Gamow factor enhancement of roughly 10 to the 40th over classical rates, allowing the proton-proton chain to sustain the sun's luminosity of 3.8 times 10 to the 26 watts for 4.5 billion years. GPS satellites experience special relativistic time dilation of -7 microseconds per day and general relativistic gravitational time dilation of +45 microseconds per day for a net clock gain of 38 microseconds per day, requiring factory frequency, offset of the satellite atomic clocks from 10.23 MHz to 10.2 299999543 MHz as implemented. From the first GPS satellites in the late 1970s and documented by Ashby in Physics Today in 2002, carbon-14 undergoes beta decay with a half-life of 5730 plus or minus 30 years via weak interaction conversion of a neutron into a proton with tunneling through the nuclear barrier, enabling radiocarbon dating developed by Willard Libby in the 1940s and awarded the Nobel Prize in 1960 with a method validated on samples ranging from Egyptian barge wood to Dead Sea Scrolls. LEDs emit photons with energy determined by the semiconductor band gap with direct gap materials like gallium arsenide 1.4 eV, gallium phosphide 1.8 eV, and gallium nitride 3.4 eV, emitting infrared, red and blue light respectively, while indirect gap materials like silicon and germanium emit primarily heat due to phonon-assisted recombination with blue LED technology pioneered by Nakamura, Akasaki, and Amano, earning the Nobel Prize in 2014. Scanning tunneling microscopes invented by Binnig and Rohrer in 1981 use quantum tunneling current across 1 nanometer vacuum gaps with exponential distance dependence, achieving sub-angstrom resolution and enabling atomic manipulation demonstrated by Eigler and Schweitzer in 1989 and awarded the Nobel Prize in 1986. Wave functions extending into classically forbidden regions. Quantum mechanics is not just theory, it's substrate. Every photon from your screen, every bit in your memory, every calorie you burn, powered by the impossible made routine. The atoms in your body, the electrons in your devices, the protons in the sun, all obeying rules that would have seemed like magic to physicists in 1800, but are engineering specifications in 2025. This is not philosophy. This is measurement. Tunneling current in nanoamps. Enzyme rate enhancement factors in the hundreds. Solar fusion rate of 10 to the 38 protons per second. GPS clock corrections to the nanosecond. Radiocarbon dates accurate to within decades over millennia. LED emission wavelengths to the nanometer. STM resolution to the angstrom. Repeatability, predictability, control. Quantum mechanics works. The universe is quantum. And the impossible happens every time you touch your phone. A 2023 paper in Advanced Science News discusses how quantum tunneling enables fusion in stars and is used to send drugs to target tumor cells in cancer therapy. Applications keep expanding. 2024 research in quantum capacitors shows energy densities of 100 watt-hours per kilogram achieved using quantum tunneling-based charge storage. Supercapacitors using tunneling reach 50 watt-hours per kilogram. Every few months, new papers in physical review letters, Nature, Science, showing tunneling in new contexts, from two-dimensional materials to biological ion channels to quantum computing qubits to energy storage. The phenomenon discovered in 1928 keeps giving. A July 2025 article at evansism.com titled "Most Stars Shouldn't Exist" argues that 95% of stars have core temperatures below the sun's. 15 million Kelvin, yet they all shine because quantum tunneling allows fusion at temperatures where classical physics says it's impossible. Without tunneling, stellar populations would be drastically different. Most stars would never ignite. The universe would be darker. Life would be rarer or non-existent. Database of the IEEE, Neil Ashby's 2002 Physics Today article on GPS relativity republished in PMC, the University of Chicago, historical records on Libby's radiocarbon dating development, the Nobel Prize, organization records for the 1986 Physics Prize to Binnig and Rohrer and the 2014 Physics Prize to Nakamura, Akasaki, and Amano, and the 2025 Physics Prize to Clark Martinez and Deverett. The post-Act July 2025 Physical Review Letters paper on Under the Barrier Recollision in Tunneling, Judith Clayman's extensive publication record in the Journal of the American Chemical Society and European Journal of Biochemistry on enzyme tunneling, the MIT News. July 2010 explainer on band gaps, Wikipedia entries on quantum tunneling, flash memory carbon-14 GPS error analysis, and light-emitting diode physics all updated. Between October and December 2025, the Big Think January 2025 article by Ethan Siegel on quantum tunneling in the sun, research papers in natural sciences. In 2023, in PMC articles on enzyme catalysis, hydrogen tunneling. IAPUS, March 2023, educational article on GPS relativity, Science Daily, December 14, 2025. Breaking news on electron tunneling discovery at PostDec. All factual, all documented, all verifiable. This is not speculation. This is the state of knowledge as of December 2025. The universe runs on quantum mechanics. Tunneling is fundamental. And every atomic trick described in this script is measured, repeated, published, peer-reviewed, and engineered into devices you use every single day. The impossible is infrastructure. Welcome to the quantum age.